Hang a steel paperclip from a magnet and play a blowtorch flame on it. At some moment it lets go and drops, as though somebody had switched the magnet off. Let it cool and it jumps back up. And here is the part worth an hour. The paperclip does not fade as it warms. There is a temperature, for iron 1043 Kelvin, where the magnetism reaches 0 and stays. Plot magnetization against temperature, and the curve comes down onto the axis with a vertical tangent, then runs flat forever. A corner at a temperature a torch can reach.
Hold on to the corner because it is the whole subject, and no small system is permitted to have one. But start where we stopped. Last time was an hour on the case where nothing happens.
Where nothing happens, and it took the whole hour to earn. Turn the interaction on gradually, and every state of the free gas slides into a state of the real metal, none appearing, none vanishing, so the catalogue survives. Adiabatic continuity, a hypothesis with named ways of failing.
Named ways of failing, and today is what happens when it fails. Not fails in the sense that the arithmetic gets harder, fails in the sense that on the way down in temperature, the system stops deforming and does something with no counterpart in the catalogue at all. It picks. There is a family of arrangements the Hamiltonian genuinely does not distinguish between, and below a certain temperature, the system is in one of them and not the others, and every atom in a centimetre of metal agrees about which one.
Which sounds like the sugar molecule from our first hour with more participants. You told me last time it is not, in 3 specific ways, and I want to hold you to all 3 because otherwise this is a repeat, and I will say so.
3 ways, and they are the agenda. 1. A sharp temperature. Sugar has no critical point at all, it is simply stuck, and was stuck at every temperature you could have asked about. Iron has a temperature at which something happens, and the something is a genuine mathematical singularity. 2. Sugar chose between 2 options, left hand or right hand. Iron chooses from a continuous family, every direction in space, so a sample can point one way here and a hair's breadth differently a millimetre away. 3. Which follows from 2. Iron has excitations no molecule can have, slow twists of the choice itself, costing arbitrarily little, and a stiffness that makes a centimetre of metal answer a twist as one object.
Which of the 3 is the paperclip actually showing me when it drops?
The first, and we should go further back than the drop. Above the Curie point, what is actually going on inside the iron?
Every atom still carries a magnetic moment. They point in every direction, uncorrelated, so the total comes to nothing. There is nothing to report because the average is 0, not because the magnetism is gone.
That distinction is the beginning of everything. The disordered phase is not quiet. It is loud and disagreeing. What is 0 is one particular average. So we want a quantity whose whole job is to be exactly 0 in the disordered state, non-zero in the ordered one, and to say both how much of a choice was made and which choice it was.
For a magnet, the candidate is obvious. The magnetization, the total moment divided by the volume.
Obvious here and not obvious in the next material. So notice what made it right, because you need the criteria rather than the example. 0 above, non-zero below. Not a single number but a vector carrying a direction, and the direction is which member of the family the system settled into. And, the property people skip, it must change when you apply the symmetry you claim is broken. Rotate every spin, and the magnetization rotates with them. A quantity that sits still under the symmetry cannot be measuring the breaking of it.
What is it called?
The order parameter. Landau's word, 1937, and I want to be blunt about its status. It is not a definition you apply mechanically. It is a guess, the most consequential guess you make about a state of matter, and everything downstream inherits it. Guess wrong, and your theory predicts nothing.
Show me a case where the guess is hard, because a magnet will not convince me it is hard.
In increasing order of pain, then. A crystal first. What broke when the liquid froze?
Translational symmetry. The liquid looks the same from every point. The crystal only from points a lattice vector apart. So the order parameter measures how lumpy the density is, how much of it sits at the lattice's own periodicity.
And make that concrete because we lean on it later. A reciprocal lattice vector is nothing more exotic than a family of parallel atomic planes named by the direction they face and how far apart they sit. So a crystal's order parameter is a list of numbers, one per family of planes, saying how strongly the density ripples across that family, each carrying a phase that says where the planes sit. Far stranger than a magnetization for the most familiar transition there is. Next, a superfluid, whose order parameter is one complex number, an amplitude and a phase, and the phase has no classical meaning whatsoever. Last, the pseudo-gap phase of the underdoped copper oxides. Something happens at a temperature you can put on a phase diagram, and after 4 decades there is no agreed order parameter, and a live position that there is nothing to find.
The symmetry is broken. Does that mean the symmetry has gone?
Not remotely, and the sloppiness costs people years. The symmetry is exactly where it was. Every term in the Hamiltonian of a lump of iron is unchanged if you rotate all the spins together. Still true below the Curie point, at every temperature, forever. What changed is the state. Apply the rotation to a magnetized sample, and you do not get the same state back. You get a different state with precisely the same energy.
So the symmetry has stopped being a statement about one state and become a statement about a family of them. The set of ground states is symmetric. No individual member of it is.
That is the sentence, and if you hold one thing from the first quarter of this hour, hold that. Every direction on a sphere is a perfectly good ground state of iron, all exactly degenerate, and the sample is sitting in one of them.
How does a corner get into a smooth problem?
Not by solving anything, and let me say what we are giving up before we start. Nobody can compute the free energy of a lump of iron from its Hamiltonian. What we can do is refuse to try, and ask instead what shape it is forced into, and the shape turns out to carry nearly all the content.
Define the object carefully first. Is that a real quantity or a device?
A real quantity. Pick a value for the magnetization. Sum over every microscopic configuration of the sample that has that value and no others. Every arrangement of every spin consistent with the constraint, with the usual Boltzmann weights. Then take the logarithm with the usual minus temperature in front, so that low free energy means many configurations. That gives a number for each value you might have picked. At each temperature, you have a function. Free energy against order parameter.
And the state the system is actually in is the value that minimizes that function.
The value that minimizes it, in the limit of a large sample, which is the only place the corner lives. In a finite sample, the honest free energy sums over every value of the order parameter instead of picking the best one. And a sum of finitely many smooth things is smooth. Li and Yang from our first hour. Minimizing is what survives in the large sample limit. Now, what shape is the function?
I have no idea. That is precisely what I cannot calculate.
You do not need the whole shape. You need it near the transition, and there you have a gift. The order parameter is small. It is 0 just above, and just below it has only had a moment to grow. So expand in powers of it and keep the first few terms. That is the only assumption in the construction, and it is the one that comes back to bite us at the end of the hour.
Write the general expansion for me, a constant term, plus something times the order parameter, plus something times its square, plus its cube, plus its fourth power, and onwards.
Now use the symmetry. In a magnet with no field applied, Is there any difference at all between magnetization pointing up and magnetization pointing down?
None. They are mirror images, and the Hamiltonian cannot tell them apart, so they must have identical free energy. Which means the function has to give the same answer for a value and for minus that value. And that kills terms. Every odd power changes sign when I flip the order parameter, so every odd power has to have coefficient 0. The linear term goes. The cubic goes. What survives is the constant, the square, the fourth power, and up.
That is the most important step in this hour, and notice how little you used. Not quantum mechanics, not the Hubbard model, nothing about iron. Only the statement that up and down are equivalent. Symmetry deleted half the terms.
And the constant is everything not about the ordering, the lattice, the core electrons, the rest of it. It does not depend on the choice, so it only moves the 0 of energy. Throw it away.
Throw it away. So you are left with two terms, and now we interrogate them one at a time. Start with the coefficient of the square. Suppose it is positive. What does the function look like?
A bowl, smallest at 0 order parameter, rising in both directions. So the minimum is at 0. The system has made no choice, and that is the state above the Curie point.
Now suppose it is negative.
Then it is an upside-down bowl near the origin. 0 is now a maximum. The system is balanced on a hilltop. Any tiny magnetization lowers the energy, so it grows. Which is the ordered state trying to happen.
So that one coefficient decides which phase you are in, and the transition is the temperature where it passes through 0. Now the boldest step in Landau theory, and I want it labelled as a step and not smuggled through. We assume that coefficient crosses 0 as a straight line in temperature.
You cannot do that. A straight line is the smoothest object there is, and you have run it through the one point in the problem where I expect smoothness to fail. That is not an approximation. That is assuming the answer.
Less than you think. I am not claiming the coefficient is a straight line everywhere. It is some function of temperature that happens to vanish at one point, and I am asking only about temperatures immediately either side of that point. Close enough to a simple 0, nothing survives but the slope. That is an assumption about a neighborhood, not about the transition.
The defense works, and it still cannot be right, because your neighborhood is exactly where the trouble is. If something here stops being smooth, it will not do it somewhere convenient.
It will not, and it does not. You have found the crack in the foundations from the inside, and I am going to leave it open and come back to it in the last quarter of the hour. For now, the coefficient of the square is proportional to how far you are above the critical temperature. Positive above, negative below, 0 at it. Now the fourth power term. Why do we need it?
Because below the transition, the quadratic term alone is a disaster. It is negative, so the bigger the magnetization, the lower the energy. Without limit, the system would magnetize to infinity. Something has to grow faster and push back.
And the next term symmetry allows is the fourth power. Give it a positive coefficient and it dominates at large order parameter, so the runaway stops at a finite value. And we need no temperature dependence from it at all. The quadratic coefficient is doing all the varying, so evaluate the quartic one at the transition and leave it there.
So I have the whole function. Can I find the minimum myself?
Then do not minimize anything. Two terms, one negative going as the square and one positive going as the fourth power. They have to balance. That is the whole calculation.
If they balance, the square of the order parameter is proportional to the negative coefficient divided by the positive one. And the negative coefficient goes as the distance below the critical temperature. So the square of the magnetization is proportional to how far below the transition I am. and the magnetization itself goes as the square root of the distance below the Curie temperature.
A square root. And now cash it against the thing you walked in with.
A square root leaves 0 with an infinite slope, which is my corner. The magnetization rises out of the axis vertically, bends over, and above the transition it is flat 0. From symmetry and 2 coefficients, I never needed to calculate.
That is the point of the construction. Now the picture as well as the exponent, because the picture is what you will remember. Above the transition, free energy against order parameter is a bowl with its lowest point in the middle. Cool through, and the bottom of the bowl pushes upward into a dome. The lowest points are no longer in the middle. They are out at a ring around it.
And because a magnet's order parameter is a vector in 3 dimensions, those are not 2 points at the ends of a line. They are a whole sphere of directions, all at the same depth.
The bottom of a wine bottle. The punt pushed up into the base with the circular trough around it. That is the most useful picture in this subject, and it reappears in every remaining hour of this series. The system is a marble in that trough. Every point is as good as every other, and the marble is in one of them.
What have we built? Because it feels assembled rather than handed over.
Landau theory. Lev Landau, 1937, 2 papers, written when he was 29. A year later, he was in the Lubyanka, and he came out only after Kapitsa wrote to Molotov and put up his own personal guarantee for him. Say back what the theory is made of, because the shortness of the list is the whole argument.
An expansion of the free energy in powers of a small order parameter. Odd powers deleted by symmetry. A quadratic coefficient, changing sign at the critical temperature, crossing linearly. A positive quartic stopping the runaway. 2 numbers I never calculated, and the shape falls out.
And one more thing falls out for free. Apply a magnetic field. What does it do to the picture?
A field couples to the magnetization, so it adds a linear term. The odd term symmetry deleted, put back by hand because the field breaks the symmetry itself. And a linear term tilts the surface, so one side of the trough is lower and the marble has a preference.
Tilt the wine bottle. And the 2 limits from our first hour follow in a clause. Tilt it infinitesimally and grow the sample, and the marble is trapped at the low side long before the tilt comes off, because the barrier between the sides is the cost of splitting the sample into 2 regions pointing different ways, and that grows with the area of the wall between them. In a centimetre of iron, that barrier is not large. It is unclimbable.
Which is why the choice, once made, is permanent. What is the caveat?
That not one line of this was derived. Landau did not compute the quadratic coefficient, or the quartic one, or the critical temperature from any microscopic model, and nobody has since for iron. It is the bargain from our first hour, and the bargain from last time, a framework with unknown coefficients that constrains a great many relationships between measurements, while producing none of them itself. Same man, incidentally, 20 years apart.
The symmetry step did more work than anything else in that build. What happens if the cubic term is not forbidden?
Everything changes, and this is one of the sharpest predictive statements in the subject. Put a cubic term back. It is odd, so it favors one sign of the order parameter, and it grows faster than the quadratic term. What you get is a free energy with a minimum still at 0, a second minimum out at some finite order parameter, and a ridge between them.
2 minima at different depths, and as I cool, their depths change relative to each other.
At some temperature, the outer one drops below the central one. Before that moment, the system sits at 0. After it, the true minimum is out at a finite value. What must happen?
It has to jump. There is no continuous path because the values in between are up on the ridge. So the order parameter is discontinuous at the transition.
and a discontinuous order parameter drags a family of everyday consequences behind it. Name what you would see in the laboratory.
If the order parameter jumps, the entropy jumps, so heat goes in or out at fixed temperature. Latent heat. Both phases exist at once while it does, and with a ridge there, the system can sit in the wrong minimum, cool past the transition, and nothing happens until something starts it.
All of it. And these are the transitions everybody meets first. Melting a gram of ice takes about 330 joules, with the thermometer refusing to move. Boiling a gram of water takes about 2,300. Supercool, very pure water below 0 degrees Celsius, and it sits there, liquid, until a speck of dust gives it somewhere to start. 1 discontinuity, 4 familiar phenomena.
And the transition I have spent the last 20 minutes on has none of those.
None. A continuous transition has no latent heat, no coexistence, no hysteresis, no nucleation. The order parameter grows continuously out of 0. These were called second order and first order after Ehrenfest's classification. The modern names, continuous and first order, are better because they say what happens rather than counting derivatives.
When is the cubic term allowed? Symmetry killed it for a magnet, so what is the rule?
Landau's own rule, and it is checkable. A continuous transition is only possible if symmetry forbids a cubic invariant built from the order parameter. If one is allowed, the transition is first order, essentially always. Now apply it to the most familiar transition in the world, a liquid freezing.
The order parameter was that list of density ripples, so a cubic term is a product of 3, and for the product to be a number rather than a wave that averages away, the 3 vectors naming those planes must add up to nothing.
Can you find 3 that add to nothing?
Easily, in almost any lattice, 3 of them forming a closed triangle. A triangular lattice has them immediately, and so does a body-centered cubic one. So the cubic term is allowed, and freezing has to be first order.
Freezing has to be first order, which is why ice melts at a temperature with heat pouring in and never over a range. And here is the consequence people find surprising. The liquid-gas line ends. 647 Kelvin and about 220 atmospheres for water, and above that there is no distinction between liquid and vapor. The solid-liquid line does not end. Push the pressure as high as you like, and the boundary is still sharp, because a symmetry either holds or it does not, and there is no interpolating between having a lattice and not having one.
That is a real prediction from an argument with no physics in it beyond counting vectors, and I did not expect one to come out.
It is the sharpest thing the method does, and it costs nothing to check. Hold on to it, because we now go looking for what else that trough is obliged to produce.
You promised excitations that cost almost nothing. Where do they come from?
Straight out of the wine bottle, and you can see it before I say anything. There are 2 kinds of direction the marble can move. Name them.
Up the inner dome or up the outer wall. Radially, changing the size of the order parameter. That costs energy. Or round the trough, changing the direction and not the size. And round the trough is flat. That costs nothing.
Exactly nothing. And it has to, because going round the trough is applying the broken symmetry, and applying a symmetry cannot change the energy. That is not an approximation, it is a definition. So one of the 2 kinds of motion is free.
Only that is a rotation of every spin in the sample at once, which is not a wave and not an excitation. It is just a different ground state.
Which is the objection to have, and it is 1 step from the answer. And the step is the hinge of this whole hour. The trough is not one object sitting somewhere. There is a trough at every point of the sample, each with its own marble at its own angle. So the order parameter has an angle everywhere in real space, and the mode we want is that angle varying from place to place. Rotate them all alike, and you have another ground state. Rotate them differently, and you have an excitation. Ask what that costs.
A line of compass needles then, each wanting to be parallel to its neighbours, a pair out of line, costing the square of the angle between them. I fix one end, rotate the far end by a quarter turn, and let the rest do what they like.
They will share the twist out evenly. Now count.
With 1,000,000 needles, each neighbouring pair is out of line by 1,000,000th of a quarter turn. The cost per pair goes as that angle squared, so it is 1,000,000th of 1,000,000th. And I have 1,000,000 pairs, so the total is 1,000,000th of what a single sharp twist would have cost. Spread the twist further and it gets cheaper without limit.
Without limit, and there is the mode. A rotation of the order parameter that varies slowly in space costs an energy that goes to zero as the wavelength goes to infinity. So there is an excitation whose energy can be made arbitrarily small, and nothing had to be tuned or cooled to arrange it. Break a continuous symmetry, and you get a gapless mode for free.
Say gapless precisely because it is doing work.
There is no minimum price of admission. In most systems, to excite anything at all, you pay some finite energy, a gap, and below that the system is inert. Here there is no floor. Whatever budget you have, there is a mode you can afford. Which is why these modes are the only things left at low temperature, and why they control every ordered phase there is.
And the other direction, up the wall of the trough?
Gapped. That is a wave in the magnitude of the order parameter rather than its direction, and it costs a finite energy, however long its wavelength, set by the curvature of the wall. People call it the amplitude mode, or the Higgs mode, by analogy with the particle physics version. It has been seen, and it is far harder to catch than the free one, for the obvious reason.
What is the free one called, and whose is it?
In a magnet, it is a magnon, or a spin wave. Felix Bloch had those in 1930, decades before the general theorem. The general statement is the Goldstone theorem. Break a continuous symmetry in a system with short-range interactions, and you must get a gapless mode. Jeffrey Goldstone, 1961, in Nuovo Cimento, in Field Theories with Superconductor Solutions, and the title is the tell. Yoichiro Nambu got there first from the other side in 1960, taking the theory of superconductivity and asking what it meant for particles. He had the Nobel Prize for it in 2008. Goldstone, Salam and Weinberg proved it in 1962.
Can you give me the recipe as an algorithm? You promised I could do this on a phase I have never seen.
Count the flat directions. Look at the family of degenerate ground states, the trough, and ask how many independent directions you can move along it. That is how many gapless modes to expect. Try it on a crystal.
A crystal broke translation symmetry, and I can slide the lattice in 3 directions without changing anything. 3 flat directions, 3 gapless modes. And a slow variation of where the lattice sits is a displacement wave. Sound, 3 acoustic branches, 1 longitudinal, 2 transverse.
Sound is the Goldstone mode of a broken translation, which closes a loop from our first hour. Sound was the tame example of an effective theory, a stiffness, a density, a square root, 5,000 meters per second in aluminium. It is also the leftover of a symmetry the crystal destroyed when it froze. Sound exists because space stopped looking the same from every point. Now find the edge of the recipe, a magnet whose spins have only 2 states, up and down, nothing in between. How many flat directions?
None. There is no trough at all, 2 separate pits with a ridge between them, and I cannot slide from one to the other at any price short of climbing, so no gapless mode.
None. And that is where the word continuous in the theorem earns its keep. A discrete symmetry hands you a choice with no continuum to drift along, so there is nothing to twist slowly and nothing free to excite. Same lattice, nearly the same physics, and one has a magnon and the other does not.
On the case we actually care about, I think the recipe fails. Iron's order parameter is a vector, so the ground states form a sphere of directions, a two-dimensional surface, two flat directions, two magnons.
And a ferromagnet has one. So the recipe as stated is wrong, and the reason is worth the detour, because it is the one genuinely subtle piece of this.
Why? Count the flat directions was the whole algorithm.
The two flat directions of a ferromagnet are not independent coordinates. They are a coordinate and its momentum. The order parameter of a ferromagnet is the total spin, which is conserved and which is itself the thing that generates the rotations you just broke. That is what forces the two transverse components to be canonically conjugate, exactly the way a position and a momentum are. And a coordinate together with its own momentum is one oscillator, not two.
So the two collapse into one, and that should change what the mode does, not just how many there are, because a coordinate paired with its momentum does not vibrate back and forth, it goes round.
It precesses. A magnon in a ferromagnet is a precession wave, each spin sweeping out a small cone, with the phase advancing as you walk across the crystal. And precession is why its energy rises as the square of the wave vector rather than in proportion to it. The control case is an anti-ferromagnet, where neighboring spins alternate. Its order parameter is the difference between the sublattices, which generates nothing and is not conserved, and it has two magnons, both with energy proportional to wave vector.
Which is the same broken symmetry giving two different answers depending on what the order parameter is doing in the Hamiltonian. That is not a detail, that is a different theorem.
It took until 1976 to sort out, Nielsen and Chadder, on how to count Goldstone bosons. Sort the modes by whether their energy goes as an odd or an even power of wave vector. Count the odd ones once and the even ones twice, and the total is at least the number of broken symmetries. Iron's one quadratic magnon counts twice, and the books balance.
You get a gapless mode for free is exactly the kind of statement that turns out to have conditions attached. What are they?
Two, and both matter. The first is short-range interactions, which I put into the theorem deliberately. If the force between the constituents is long-ranged, the argument fails, because a long wavelength distortion is no longer cheap. Every part of it is talking to every other part. In a metal, that is why the plasma oscillation keeps a finite frequency at long wavelength instead of going soft. And in a superconductor, where the broken symmetry couples to the electromagnetic field, the would-be Goldstone mode is pushed up to finite energy and swallowed by the photon, which acquires a mass inside the material. Philip Anderson, 1963. Plasmons, gauge invariance, and mass. A year before the particle physics version. Two conversations from here.
And the second? Because iron has preferred axes, you said the cube edges, which sounds like it should spoil the flat trough.
It spoils it, and the size of the spoiling is the whole story. Spin-orbit coupling ties the spins weakly to the crystal axes, so the trough is not perfectly flat. It has shallow scallops in it. The anisotropy is a few millionths of an electron volt per atom against an exchange scale near a tenth of an electron volt. The crystal breaks the symmetry at one part in tens of thousands, and a magnon in iron has a small gap rather than none. The Goldstone mode is a statement about an idealization. Keep that scallop, it comes back at the end, and it is not a footnote.
How do you actually see a magnon? Everything so far has been argument.
You throw neutrons at it. And let me motivate the choice rather than assert it, because the reasoning is lovely. What do you need from a probe that is going to map an excitation in a crystal?
Two things at once. To resolve structure on the scale of the lattice, a wavelength of about an ångstrom. To measure the excitation's energy, resolution of millielectron volts. So the probe's own energy must be about that, or I am hunting a tiny shift on a huge number.
And that pair is much harder to meet than it sounds. An X-ray of 1 ångstrom wavelength carries about 12,000 electron volts, so seeing a milli-electron volt shift means measuring to 1 part in 10 million, which people now do, heroically, at synchrotrons. An electron has the right wavelength but stops a few atomic layers into a solid. Now take a neutron in equilibrium with a room temperature moderator.
Its energy is thermal, about 25 thousandths of an electron volt. And a neutron is heavy compared with an electron, so at that energy its de Broglie wavelength is short.
About 1 8/10 of an ångstrom. Both requirements at once, from the same particle, with no cleverness at all. A coincidence of the masses, and a whole field of physics is built on it. 2 more properties. The neutron is neutral, so it ignores the electron clouds and goes clean through centimeters of solid, probing the bulk and not the surface. And it has a magnetic moment, so it does talk to the spins.
What does the measurement look like as a procedure?
Take a beam, select a single energy from it with a crystal, aim it at your sample, then look at the neutrons coming out at a chosen angle and select a single energy from those two. You know what went in and what came out, and the differences in energy and momentum went into the sample. So you made one excitation, and you know both its energy and its momentum.
And then I scan, fix the momentum transfer, sweep the energy, find where the counts spike, repeat at the next momentum, which traces energy against wave vector directly rather than inferring it.
The dispersion relation, point by point. Bertram Brockhaus built the instrument that does it, the triple-axis spectrometer at Chalk River, and in 1957 published the first measurement of a magnon dispersion in magnetite. He shared the Nobel Prize in 1994 with Clifford Shull, who had done the other half, seeing where the order is rather than how it moves.
And Shull's case was one where nothing else would have worked, I take it.
Nothing else could have. In 1949, Shull and Smart looked at manganese oxide. An antiferromagnet has its spins alternating, so the total magnetization is exactly 0. Hold a compass to it, and it looks like nothing. Neal had predicted the arrangement, and there was no way to see it. Shull and Smart cooled below the ordering temperature, and new diffraction peaks appeared, saying the magnetic repeat was twice the atomic one. An order parameter made visible in a state with no net moment.
Give me numbers for iron. What does a magnon actually cost?
The energy at long wavelength rises as the square of the wave vector, with a coefficient of about 280 milli-electron volts times ångstrom squared. Shirane and colleagues in 1968, confirmed by Mook and colleagues later. And one limit, above roughly 85 milli-electron volts, the spin wave in iron stops being clean, because it runs into the continuum of ordinary electron-hole excitations and dissolves into it.
Can I get something out of that with no apparatus at all? Thermal energy excites magnons, each one a unit of spin flipped over. So a ferromagnet's magnetization should fall below its 0 temperature value by the number present.
So count them, and calibrate the method first on something already settled, phonons in a crystal, where the heat capacity dies as the cube of temperature. I asserted that last time and did not show you why. Start with which modes you can afford.
A phonon's energy is proportional to its wave vector, so I can afford modes out to a wave vector proportional to the temperature, and the number inside a sphere goes as the cube of its radius. So the phonons awake go as temperature cubed.
Good. Now turn a count of modes into a heat capacity.
Each carries roughly the thermal energy, so the total energy goes as temperature to the 4th. Heat capacity is how energy changes with temperature, so it goes as the cube, which is Debay's law, so the method is sound.
The method is sound. Now run it on magnons and notice the single thing that changes.
The dispersion. A magnon's energy goes as the square of the wave vector, so I reach only to the square root of the temperature. Cube that radius and the count goes as temperature to the 3 halves, and each magnon removes 1 unit of spin, so the magnetization falls by the same power.
Which is Bloch's law, 1930, and it is measured in every ferromagnet at low temperature. You derived it by counting, from a dispersion relation a neutron beam handed you, and the only difference from the phonon case was 1 exponent. And notice what became of the sea of 10 to the 23 spins. It vanished. All that is left is a dilute gas of the cheapest excitations, and the thermodynamics belongs to them.
Rigidity. You promised it in our first hour and called it the same idea as the mode, not a second one. Can you get it out of the same picture?
The same picture run backwards, and the whole thing is in the compass needles you already built. You twisted them. You worked out what it cost. Now do the same sum in 3 dimensions instead of 1, and be careful about the volume.
A cube of material. Hold the order parameter fixed at one face. Rotate it by a fixed angle at the far face. The twist shares out evenly, so the change of angle with distance is the angle over the size, and the energy density goes as the square of that. So energy per unit volume goes as angle squared over size squared, and volume as size cubed.
Multiply.
The size cubed over the size squared leaves 1 factor of the size. So the total energy goes as the angle squared times the size. It grows with the sample.
Say what that means physically, and slowly, because that one line answers a question people ask for years.
I cannot twist a large sample by a fixed angle cheaply. The bigger the lump, the more it costs. So the choice the system made is not merely made, it is defended. And defended harder the more material there is. No local disturbance can argue a macroscopic sample out of its direction, because a disturbance has a fixed budget, and the twist costs in proportion to size.
That is rigidity, and it is the whole of it. Now run the same sum in 1 and 2 dimensions, because it costs you nothing.
In 1 dimension, the volume is just the length, 1 factor of size against 2 below, so the cost falls to 0 as the sample grows. A long chain twists itself apart. In 2 dimensions, the factors cancel, and a twist costs the same at any size. So 2 is marginal.
2 is the marginal case, and there is a theorem sitting on it, though what you just did is not the proof. You priced a single twist, which is a statement about 0 temperature. The proof counts how many of those cheap modes are thermally awake at once, and that is where the 2nd dimension bites. Mermin and Wagner, 1966. In 1 and 2 dimensions, a system with short-range interactions and a continuous symmetry cannot have long-range order at any temperature above absolute 0. The modes you got for free are numerous enough to eat the order that produced them. Hohenberg had the same for superfluids at the same moment.
Where do I see this in something I can touch?
Take them one at a time, and tell me the broken symmetry each time. Start with the most familiar. A steel bar resists being sheared. Why?
A shear is the twist I just did. Top face displaced sideways relative to the bottom, varying smoothly between. A solid broke translational symmetry, so the displacement field is the order parameter's freedom, and a shear is its gradient. Same argument, same stiffness.
The shear modulus of a solid is the order parameter stiffness of a broken translational symmetry. Steel is about 80 gigapascals. And now the negative case, which is what makes it a real statement.
A liquid never broke translational symmetry, so it has no order parameter to be stiff, so it has no shear modulus. Which is the definition of a liquid? It does not resist a static shear at all, not weakly at all.
the cleanest instance in the subject, a phase distinction you can feel with your hands, and what separates them is whether a symmetry got broken. Next, why does the paperclip you started with not lose its magnetization the moment somebody breathes on it?
Because reversing it means passing through arrangements where different parts point different ways, and by the same sum, a wall between two such regions costs energy proportional to its area. So flipping the sample means paying a wall to sweep across it.
And a real domain wall in iron is a measured object. Tens of nanometers thick, 100 atomic spacings or so, because the exchange wants it spread out and the anisotropy wants it thin, and the compromise costs a few millijoules per square meter. That is where permanent magnets come from, and magnetic recording is the engineering of that number.
And the third instance, which you have been trailing since our first hour,
A superfluid flows forever. Its order parameter is a complex number. The broken symmetry is in the phase, and a flow is a gradient of that phase. A slow, steady winding as you go along the pipe. Now bend the pipe into a ring and ask what the winding has to satisfy.
the phase must come back to itself all the way round, so the winding is a whole number of turns. The current in that ring is labelled by an integer.
And that is why it does not decay. To reduce the current, you must reduce the integer, and an integer cannot change a little. The only way to lose a turn is to push a line where the order parameter's magnitude goes to 0. A vortex where the phase is undefined and therefore free to slip, right across the flow, wall to wall. That costs an energy set by how far it must travel, which is the width of the sample.
So superflow is not frictionless by magic. There is a decay channel, priced out by the size of the container. The twist argument again, with a whole number on top.
That is Anderson's unification, and you assembled it rather than receiving it. A solid's stiffness is against moving atoms. A superfluid's is against winding a phase. Different broken symmetry, one mechanism, and the promise from our first hour is paid.
And the connection between the two halves of this hour. Rigidity and the Goldstone mode feel like one thing wearing two hats.
One number seen twice. The stiffness that resists a static twist is the coefficient that prices a slowly varying twist, and therefore the coefficient that sets the frequency of the propagating one. In a solid, that stiffness over the density, square-rooted, is the speed of sound. The formula from our first hour. Ask what it costs to bend the order, and you get a modulus. Ask how the bend propagates, and you get a Goldstone mode.
The thing I flagged an hour ago. You wrote the free energy as a power series, with a coefficient crossing 0 as a straight line. Smoothness assumed at exactly the point where I expect it to fail.
And I want to state the failure more carefully than most treatments do, because the loose version is unfair. Landau theory does not assume the transition away. It writes the constrained free energy as analytic, and minimizing then produces a genuine singularity. Your corner is real, and it came out of smooth ingredients. The trouble is subtler. Below 4 spatial dimensions, the constrained free energy is itself not analytic, so the series was never entitled to exist. And the singularity the method does produce is the wrong kind.
Why does it get anything right at all then?
Because it gets the structure right and the numbers wrong, and the structure is most of what you want. It tells you which transitions can be continuous, what symmetry the ordered phase must have, that there is an order parameter growing out of 0, that there are Goldstone modes and rigidity, and what a field does. What it gets wrong is the immediate neighborhood of the transition.
Where is the physical error, though? The function is not analytic, is a symptom, not a cause.
The physical error is assuming each part of the system feels the average behavior of the rest. That predates Landau by 30 years. Pierre Weiss, 1907, put each atomic moment into an internal field proportional to the average magnetization of the whole sample and got a Curie temperature out of it. Pierre Curie had measured the phenomenon in 1895. It is called mean field theory, and Landau theory is its general form.
Near the transition, there is no meaningful average then, because a spin feels its own correlated neighborhood rather than the sample-wide mean. But here is what I cannot see. Why should those regions grow? Why does approaching the transition make patches bigger rather than the order weaker?
Because the coefficient that punishes ordering is the one going to zero. Above the transition, the free energy is a bowl, and its curvature is the price of pushing the order parameter away from zero. Make a patch of order, and you pay that price over the volume of the patch, and the curvature drags it back. Now cool, the bowl flattens, the price of ordering a patch falls, so the patch you can afford for nothing grows. And at the transition, where the curvature is exactly zero, there is no price at any size.
So the theory carries its refutation in the term it is built on. One flattening bowl, two consequences, and they are opposed.
That is exactly it. Landau's quadratic coefficient predicts the divergence that destroys Landau's own exponents. The sample near the transition is a froth of ordered patches of every size at once, and mean field theory replaces the froth with a single number.
Has it been caught being wrong, though? An argument that something must fail is weaker than a demonstration that it did.
Caught three ways. First, exactly. Lars Onsager solved the two-dimensional Ising model in 1944. Spins on a square lattice, two states each, nearest neighbor coupling. And there the magnetization grows, not as the square root of the distance below the transition, but with an exponent of 1/8. Onsager stated it and never published the derivation. Chen-Ning Yang did in 1952.
1/8, and I can see what that does to my curve. A square root leaves the axis vertically, then bends over slowly. 1/8 leaves far more violently, magnetization nearly at full strength, while the temperature has barely moved. Not my corner with a new number on it. A sharper corner.
A sharper corner, and no adjustment of Landau's two coefficients, will bend a square root into it. Second, experiment, before anybody understood it. Guggenheim, 1945, took the measured coexistence curves of 8 fluids: argon, krypton, xenon, neon, nitrogen, oxygen, carbon monoxide, methane, plotted each in units scaled to its own critical point, and found they all fell on one curve. Startling in itself, and we come back to why. The exponent of that curve was about 1/3.
An exact solution and a bench of liquefied gases, both between 1/8 and 1/3, neither near a half. What do modern numbers say for the systems we have been discussing?
For a three-dimensional magnet whose spins have two states, about 33/100ths. Where the spins can point anywhere, as in iron, about 37/100ths, never 1/2. And the most precisely measured critical exponent in physics is not a magnet at all. It is the heat capacity exponent of liquid helium at its superfluid transition. Before I tell you the number, work out where that measurement had to be made.
Somewhere without gravity, if they were pushing that close in. The sample has weight, so its bottom sits at higher pressure than its top, and the transition temperature depends on pressure, so different heights cross at different moments. The singularity gets smeared across the cell by the fluid's own weight.
Which is why the helium flew. Space Shuttle, 1992, analysed for a decade afterwards by Leaper and colleagues, about -13 thousandths, from data within a couple of billionths of a Kelvin of the transition. Mean field theory predicts a clean finite jump in the heat capacity, and that is not what a small negative exponent looks like.
Why is mean field theory not simply discarded then? You have spent an hour on it, and people use it constantly.
Because whether it fails is quantitative, and the answer turns on how many neighbours each part of the system is effectively averaging over. Ginzburg wrote the criterion down in 1960. Compare the fluctuations of the order parameter within a correlated region to the order parameter itself, and mean field theory is fine wherever the fluctuations lose.
And that comparison depends on what?
On how far the correlations reach, and the extreme case is where this series is heading. In an ordinary superconductor, the correlation length is enormous, hundreds or thousands of angstroms, so each pair averages over millions of others. Ginzburg's estimate for the width of the region where mean field theory fails, there is 1 part in a million of the transition temperature.
Which nobody will ever measure, and I can see why the averaging works so well there. If each pair overlaps millions of others, the fluctuation anyone feels is diluted by that count before it can do damage.
Which is why the mean field theory of superconductivity is for practical purposes exact. In liquid helium, the correlations are short, the critical region is wide, and the exponents are measurably not mean field, which is how Lipper had anything to measure. Same framework, 2 materials, one exact and one visibly wrong, and what separates them is a length.
And presumably there is a statement in terms of dimension, since dimension has decided everything else today.
There is, and it belongs to a later conversation. Mean field theory is exact above 4 spatial dimensions and wrong below. 4 is the upper critical dimension. Why there should be such a thing, why the wrong exponents come out identical for a magnet and a fluid with nothing in common, and why Landau's picture ends up rescued rather than discarded. That is the renormalization group, 3 conversations from here. On the record now, the exponents in this hour are wrong. They were known to be wrong for 30 years before anybody could fix them. And the fixing is one of the deepest things in the subject.
I would rather finish by finding out whether I can use any of this. Give me phases I have not seen, and let me call them.
Gladly, and I will correct you where you need it. First, a nematic liquid crystal. Rod-shaped molecules in a fluid, which below a certain temperature agree to lie along a common axis while still flowing freely past each other. Name the broken symmetry, the order parameter, and the mode.
Rotational symmetry is broken. Translational symmetry is not. The molecules still sit anywhere. The order parameter must know about the axis, but not which end is which, since the rods have no head or tail, so it cannot be a vector. It is a tensor. The degenerate family is the set of possible axes, a sphere with opposite points identified, so 2 flat directions. And nothing conserved is playing the role the total spin played in iron, so I predict 2 gapless modes, both slow bends of the axis.
All correct, and there is an everyday consequence you can supply yourself.
Gapless modes are excited in enormous numbers at ordinary temperatures, so the axis wobbles on every length scale, including the wavelength of light. So a nematic should scatter light strongly and look milky rather than clear.
Which is exactly what it looks like, and it is why the phase was noticed at all in the 1880s. Second, a metal whose electron density spontaneously develops a static ripple with a period unrelated to the lattice spacing, a charge density wave.
Translational symmetry again, but only along the ripple. The order parameter is that wave's amplitude and phase, so there is one flat direction. Sliding the ripple along changes nothing, and one gapless mode.
A phason, and sliding the whole wave would in principle carry current with no resistance. Froelich proposed that before anybody had the real mechanism. In practice, impurities pin it. Third, and this one I expect to cost you, a single atomic layer of a magnetic crystal, peeled off with sticky tape. Spins free to point anywhere. Does it order?
It should not. Continuous symmetry, short-range exchange, 2 dimensions. Mermin and Wagner exactly, and the theorem says no order above absolute 0. A 1-atom-thick magnet should be a paramagnet all the way down.
And it is a ferromagnet. A single layer of chromium triiodide orders at about 45 Kelvin. Huang and colleagues, 2017. So something in your argument is not being paid.
A hypothesis failed, not the theorem, and only one was handed to me with instructions not to file it as a footnote. The anisotropy. Tie the spins to an axis, and the symmetry is no longer continuous. The scallops matter, the magnons acquire a gap, and a small temperature cannot excite a gapped mode without limit. The modes that would have eaten the order cannot afford to wake.
That is the correction, and you made it yourself. Notice which piece of the hour saved you. The caveat, not the theorem. In bulk iron, the anisotropy is a rounding error. In one layer, it is why the phase exists at all. A whole field standing on a term I introduced as a nuisance.
Better than 3 right answers. 2 things unprompted then. Rigidity. An ordered system defends its choice because bending the order costs energy that grows with the sample. Gradient as 1 over the size. Cost as gradient squared. Volume as size cubed. Hence a solid resisting shear, a magnet holding its direction, a superfluid current that cannot decay. And it is the mode's coefficient. A static bend is a modulus, a travelling bend is sound.
And the second?
That everything we built has an expiry date, and the date is the transition. The expansion needs the free energy smooth in the order parameter, and there it is not. The flattening bowl that gave me my square root is the same flattening that lets correlated patches grow without limit. Structure survives, exponents do not. 1/2 against 1/8 exactly solved, a third from 8 gases, the middle 30s in magnets.
That is the account, and I would rather you carried the expiry date than the exponent. Landau's expansion is not a calculation of a phase transition. It is a way of asking what a transition is allowed to be, given what the system is allowed to do. And what is allowed fixes nearly everything except the numbers people most want.
Where do we go, given that you have shown me a family of states of matter and one worked example?
To the 2 the 20th century was proudest of, which are the same idea with the order parameter swapped for something stranger. Break a symmetry whose order parameter is a complex quantum amplitude, a magnitude and a phase coherent across a whole beaker, and what you get is rigidity against changing that phase. A fluid with no viscosity climbing over the wall of its container in a film 30 nanometers thick with circulation only in whole units, for the reason you worked out with the ring.
And the second is the same thing made of charged particles.
The same thing made of charged particles, and everything changes because the phase now talks to the electromagnetic field, and the goldstone mode we spent this hour manufacturing gets swallowed whole. 2 states of matter, 1 broken symmetry, and between them most of the low-temperature physics of the last century.
So the marble is still in the trough, and the trough is about to hold something much stranger.
The trough does not change. What sits in it does. Next time it is a liquid that will climb the walls of its own container to get out, and the reason it can is 1 whole turn of a phase.